So hope you can see my screen. Is it visible to everyone? So in the morning class, we went through this attention mechanism. We have like seen like how it is happening in the case of transformer. Okay, so let's see again. Let's go for some of the other things which we have not seen, which we have not covered in the first class, in the morning class. So let us start with the setup of the transformer. Like what is the typical diagram of the transformer? So we already have seen that in the case of transformer, we have encoder block, and then we have a decoder block. So this is your encoder side, then you have decoder side. Suppose you are doing the translation. So we have given the sentence in one language, and you are going to translate it into the some other language. So this I think this is maybe French or German language, and then you are doing the translation of this into English. Okay. So what you'll do, you'll give this sentence to the encoder part of the transformer. So you can see here you are giving to the, so we have different encoder block, and in every encoder block we have the self attention mechanism that's happening here. So whatever we have seen in the previous class, so that mechanism is happening in every block here. And then this is the encoder part. So goal is to encode the information and then give to the decoder. Now you can see like from the last layer, you are taking the information and giving to the different block of the decoder. And then decoder is processing it. And finally, it is giving you the translated sentence. So you are getting sentences into English. So this is like one type of job. Your chat GPT also can also do it. You just give in one language and ask, hey, translate into this language, and it will do it. So even in the chat GPT, inside the chat GPT, this type of setup is there. Not exactly this, but similar type of setup is there. Now, let's see what are the things inside the encoder block. So one thing is your self-attention that we have seen before. And then we have feed-forward network. That's your fully connected. So self-attention followed by feed-forward network. These are the main things in the case of encoder block. So first you are applying the attention here, and once you got the like attended weighted feature vector for each word, now you apply the fully connected layer for each word separately. So this part is it can be done in a parallel, because here this feed forward network is like your fully connected network, a fully connected network. Yes. So fully connected network, now it can be applied for each word separately, because here whatever you are getting here, suppose what I have given the example that hi, how are you, and then you got the attention matrix and you multiplied it. Now you got the the feature vector of the refined feature vector of every word. So now if I say like this, these are the feature and refined feature vector of every word which you have got after this attention layer. Now if I say, hey, what is this inside this feature vector? So your answer would be, this is containing the information of hi, but it has also seen the contextual information, because you know that you have calculated the attention vector for this. So considering x1, suppose this is x1, you calculated the attention vector of attention uh, attention of attention from every other vector for this x1 vector. And this we have seen like using correlation thing. And then you have defined it. Then you have defined the feature vector of this with respect to this, this, and this. So now if I ask you like what is inside this, you will say, hey, in this, we have the information of hi, but we have also incorporated the information of this whole sentence. So it's not only information of hi, it's containing the information of high along with the contextual information or the sequential information of this sentence. Because again, high is not the separate word. High is it's giving the meaning when we have made this sentence. Okay. So that's why this high is not separate. And so that we have done this refinement of this high with respect to these all the words. Okay, now after getting this. So these are like refined vector, which is having the aggregated information of all other words along with the given word. Now I can apply fully connected layer for each word separately. Because now every word is having a lot of information. Now every vector is having a lot of information. So after this, they have applied feed-forward neural network, which can be done parallelly. And if we can do parallelly, that means this process will be very, very fast. Why? Because a, we have GPU based system, and GPU can support multiple process at a time. Okay, so this process is very, very fast. So once you are done this part, now this part is very fast. Okay, so the same thing we are seeing here. So suppose you have two words and you have given thinking. This is the first word. Second word is machine, thinking machines. And now you are going to apply self attention, like you are going to apply your this transformer over this. So what is the first goal? First goal is to convert to get the vector for each word. So you are having the embedding layer. So that will convert. So it will get x1 for thinking and x2 for the machine. Sorry. Now you give these two things to the self attention, and from the self attention, you'll find the matrix. You find the k, q, v, and then you will be having the refined feature vector for this thinking, as well as the refined feature vector for the machine. Now these are the refined feature vector, which are coming from the, like after applying the attention. That means like if I say like what is inside Z, Z1. So Z1 is containing the information of the thinking along with the information of machine as well. Because thinking is not, there is no existence of the thinking without this machine, because this whole thing make the sentence. So if you are focusing on this sentence, then every word is not giving you the, like each word is not giving you the, or maybe I can say like single word is not giving you the meaning of that sentence. So capturing the meaning of that sentence, you need to see the whole sentence. So you want to get the feature of this word, but this word is not isolated. So that's why for this word, like for this thinking word, you are taking the help from the machine, and that's why we have calculated that attention matrix. And then if with the help of attention matrix, you are giving some weight to the x2, some weight to the x1, and then you are just adding these two vector, and that is giving you the refined vector of the. Okay, so now you have defined vector of x1 and x2. So that is z1 and z2. After that, you can apply feed forward network in parallel. So, and this you are if you are applying it, that means this process is very, very fast. Okay, so this also makes this transformer fast. It's like in RNN, this type of facility was not there. You were like capturing, uh, like you have to go in a sequential manner only. So most of the time, if you go in the same block, you have to follow the sequential step only. But here, after even in the same block, this part will go in a sequential manner, or maybe here also you can do some parallelism. But after getting this thing, then whatever fully connected you are applying in this block, that can be done in a parallel manner. Because every now they are not, we are not going to find the relationship between these two, because we already have done this. Now we will separately process each vector using fully connected layer. Okay, so let's again see the same example, and we'll go one by one, step by step. This will give you the clear picture of this whole this whole self-attention mechanism. Like now, how it is happening. Again, we have seen this in the previous class also, but let's go through the example. Okay. So we have given the input, thinking, and machine. Now the first job is convert into vector. So we have embedding layer. So converted thinking into x1, machines into x2. Then we have to find q, k, and v. Q is also called queries. Again, I'll come to this part, like why this is called queries. And then key will be having keys, and then we are having values. For getting this query, we have the WQ matrix. That is your fully connected layer. For getting this uh, K, we have WK matrix, fully connected layer. And then we have for getting V, we have WV matrix. These are all the things we have seen before. And we are getting this multiplying X with WQ, that is giving you the Q. X with WK, that is giving you the K. And X into WV, that is giving you V. These are all the things we have seen in the previous class. Now I'm just opening this thing. Okay, so in the previous class we have seen these all the things in a combined manner. Now here we are doing it separately. Actually, it will happen in a combined manner only, but just for the sake of understanding, we just try to see like how individually the things are happening. Okay, so with the help of WQ, it will take the x1 and x2, and x1 will be converted into q1 and x2 will be converted into q2. And this whole thing is called as a q. So in q, we have q1 and q2. So q1 came from the x. By applying the fully connected layer on x, you got q1, like on x1. By applying the fully connected layer on x2, you got the q. Similarly, for k, we have applied the fully connected layer on x, we got k1. Like x1, we got k1. x2, we got k2. Similarly, here, like apply this fully connected layer of on x1, you get v1. On x2, you got v2. These are the things that we got. Okay. Now the thing is next thing is to find the attention matrix. Okay. So we'll go by vector. So since we have two words, so you know that you will be getting 2 by 2 matrix. That is your attention matrix. In the first, suppose this is the x1 for x1, this is for x2, this is for x1, and this is for x2. So it's like 2 by 2 matrix that we got. And if I just say like what this first matrix is giving the attention for the x1, like for the refinement of the x1. Okay. Now this is in the original space. Now if I see in this space, so what I was doing? I was doing k into q into kt. Okay. So if I just write this thing here, so again we have 2 by 2 matrix only in this case. So we have q is what? q1 and q2. So query of thinking and query of machine. And the key is like for thinking, and K1 is for thinking, K2 is for machine. Okay. Now this first vector, if you just see this first part, this is attention vector for the refinement of the first part. That is your thinking. And second one is the feature vector, the attention vector for the refinement of the machine. Okay. So now I have given this name as a queue. That is also called query. And I have given the name of this as a key, that is also called keys. So let us try to understand why this is query and why these are keys. So whenever I'm going to refine the particular word or particular input, now our job is to refine it, that input. Suppose here we are refining the thinking. So whatever you are going to refine, you will be you will be taking the query of that. That means I'm just asking the query, hey, refine this thinking. Okay. So query is going to ask the things from the keys. And with the help of that, it will get the attention values. So I'll say, hey, I have Q1 here for the thinking. That is the query. And I'm going to ask this thing from the keys. And every key will be multiplied with the query. And that will give you the attention value. So if I want to refine the first word, I'll be taking the query of the first word, that is Q1 in this case. And I have to take the keys of all these words because I'm going to ask with every other words. So your goal is to refine the X1 in the feature space. So for refining the X1, you are going to ask with X1, X2, X3, and so on. So your query is this. That is the query that query means like you are going to ask, you are going to refine that word, and that's why you are going to ask the things from every other words. Okay. So query Q1 here, and then it will be K multiply with K1, then K2, and that will give you the attention vector for refinement of the thinking. So just you can see here, we are multiplying because focus is on the key on the thinking. So I'll take the query of the thinking because query will ask, and from where, so those guys are like K1 and K2. So it will ask the things from the keys. Okay, so query 1 will be multiplied with the key 1 and you got the value. Query 1 will be multiplied with the key K2 and it got the value. So key is coming from all other words. So K1 is coming from the thinking, K2 is coming from the machines, but query is coming from the only thinking. Why? Because your goal is to refine the thinking only with the help of all other words. So that's why you're taking the query from the thinking and the keys from all other words. And then you are just calculating the attention value. Okay. So Q1 into K1. So Q1 is this, K1 is this, and that will give you this. It's just doing the dot product. Then we have Q1 here, and then we have K2 here. That is giving this value. Then again, I also said that we will be doing the normalization. So the based on the dimension. So suppose the total dimension is it's like 64. The dimension of the vector is maybe let us assume that 64. So root dk. So dk is like if dk is 64, it's just assumption. Okay, in this don't go with this example. You have to like based on the vector size, you have to decide like what is the vector size, and accordingly you will take the root of dk, and that will give the denominator part uh, for this and this. So you're going to normalize it every attention value of the matrix. So root dk, so you can see like divided by 8, you got 40, divided by 96, divided by 8, here you got 12. Now again, what I said like, hey, applied softmax after this, so that because these are not looking like a attention value, because your attention value should give value between 0 and 1. 1 is like high, very high attention, and 0 is like very low attention. So now what you'll do, you apply the softmax. So apply the softmax over these two terms. So you'll get this. Suppose you are getting this thing. Don't go with the values. It's just like this is just example that I'm showing here. Accurately, maybe the values, whatever I'm showing here, if you do it here, maybe you'll be not getting that value. But this is just example. I'm just trying to give you the process, how it is happening. So suppose you got this 0.88, 0.112. Now these are the attention values for the refinement of the thinking. Now how will do the refinement? Now you know the process. So this is you got the vector of the you got the attention vector for the thinking, and now with the help of this, suppose you got 0.88 here, 0.112 here, and now with the help of value, now we multiply this thing with value. That is your V, because value is like actual value. So we have converted into the same X has been converted into query, key, and value. So query and key are participating in finding the attention matrix, and then value is finally getting multiplied with the particular attention matrix. So now here you will be multiplying this value. So 0.88 is attention given to this part, and 0.12 attention has been given to this part. Now for this part you have value that is V1, which you have calculated at this point, and for this part you have value V2. So now you just make this the linear combination. So 0.88 will be multiplied with the V1. You can say 0.88 multiplied with V1 plus 0.12 multiplied with V2, and that will give you Z1. So you are getting Z1 here. In the similar manner, you can do the refinement of the machine also. So for the refinement of the machine, our query will be, we will be having query key 2, and then query will ask things from all other keys for getting the attention value. So query will be taken from the machine, and query will be multiplied Q2 into K1. You will be getting this thing. Then Q2 into K2. Okay. So this attention values, this will give you the attention value for the thinking part. This will give you the attention value for the machine part. And then we are going to refine the vector of this machine with the help of these attention values. Just like this, what we have done here. And here, if you do it, you will get the Z2. Now now we have seen this example. So again, now you should not, now we have seen the query key and value, so should not be confused with these all the terms. So there is meaning of that. There is meaning of query, there is meaning of keys, there is meaning of values. So query means like whom you are going to give the focus, for whom you are going to calculate the attention. So if your focus is on thinking, then query will be from thinking. And then that query will be multiplied with the keys of every other words, every words, like even including thinking also. And that will give you the attention values of thinking with respect to every other words. And then you are going to use that attention value and will multiply it with, will give like, now we are going to take the linear combination of all those words, all those vectors with the help of this attention vector. And that will give you this. Okay. So this part is more or less, I think it would be clear to everyone. Now in this, we have multi-head attention. So till now, I have just shown you the attention mechanism, like how it is happening. Now just let's see for the multi-head attention. It is called multi-head attention, and why we have used it. So actually, if if you just see carefully, when you are, suppose if I'm giving the vector of, suppose x1, vector of x2, vector of x3, and so on, then what you are doing, you are just calculating the, like this is the vector representation of this, the particular word. This is the vector representation of the particular word. This is the vector representation of the particular word. And then you are finding, like after getting query key and value, then you are finding the code, this attention matrix of every word with respect to every other word. Now what is happening here? Here your focus is on full word. So suppose if I am going to calculate the attention of x1 with respect to all other words like x1 up to xn, then I'm taking the full vector of x1, like in the feature space. I'm just leaving that part, but you'll be having query key and values. You're taking the full vector of this and full vector of this. Again, full vector of this, full vector, and then doing the dot product. So this is just like we are looking the full word and then calculating the attention vector. And then we are refining the each vector, like then we are refining each vector. Now this can be seen as a, maybe if you just recall with the fully connected layer. So in the case of fully connected layer also, we were doing the similar type of things. So we had maybe just, let us assume that one word as a one sample. So in the case of fully connected, let us assume that let us assume the image, one image as a one word. So what we are saying, we're converting this image into vector, and then we are looking full vector at a time because we had the fully connected here. And the fully connected was doing is taking it, it's like one row is getting multiplied with, maybe I should write this side. So one row is multiplied with the full vector of the x. So that's why we're getting the global information. So in this case also, just looking the full word, we are getting the global information of the word. But even we could be having some local information. Maybe we could be having the information of alphabets, which we might be losing. The same thing was happening in the case of image. So when we were applying the fully connected, it was losing the local relationship information, the local information. And that's why we have shifted to the CNN, because CNN was having the small filter size and it was just looking the a small portion of the image, a small portion of the image. And in that way, it was capturing the local information from the image. And at the end, we were just combining everything. Now, why not we should apply the similar type of strategy in this case. So for this, they came up with multi-head attention. So what is multi-head attention? Multi-head attention is very, very simple. Instead of doing one attention, now we are going to do multiple attention. So take X and divide into multiple parts. Or maybe wherever you are doing is like after conversion also you can do it. But let us see here. Let us start with this X only. So if you have X is having the this vector. Now they just in the previous case we were taking this vector as it is. Now what I am going to do, I know that this vector is for thinking. This vector is for machine, and this can be like a big vector, which is containing the information of the thinking. It's like numerical representation of the thinking. So why not I should divide into multiple parts of this vector. Okay, so that each vector will be having local information. So now this, if I just say this part is not containing the information of full thinking. It could be containing the information of maybe THI or like that. Okay, maybe this part could contain maybe some information, this information. This part could contain maybe this information. So in that manner, we have divided words into even subspace of that. And then we'll do the attention of each part, or we'll do the refinement of each part separately. So suppose you have divided, suppose you are dividing this whole vector into 8 parts. So in that case, what will happen? I'll be having eight different vectors for thinking and 8 different vectors for the machine. So I'll take the first subvector of these two vectors, and then I'll do the same process here. Like I'll apply the attention. Similarly, I'll do for this. Similarly, I'll do for this. So in that way, you will be applying this attention for these 8 words, these 8 subwords, the subvectors, we should say subvector separately. And from each subvector, after doing that, after calculating the attention and then multiplying it with the value, like all these things, all values, the process will be similar only. So we'll be getting maybe from first you are getting Z0, then Z1. For second you are getting Z1. This is for thinking, this is for machine, this is for thinking, this is machine, this is thinking, this is machine. So now you got 8 different refined feature vector for thinking and 8 refined feature vector for the machine. Now these are like separate part of the, or it's like refinement of the different parts of the thinking. Or you can, if I just consider the second part, so it's like different, the refinement of different parts of the machine. And now let us combine it. So once it's just like CNN. So you apply the CNN, and at the end you just combine all those things. So that, because at the end you need aggregated features, you need global feature. Okay, so what we'll do, once we got Z0, Z1, Z2, Z3, Z4, and Z5, Z6, Z7, and just concatenate it. Now make the big vector from this. So just concatenate it. This is for thinking, this is for machine. And then Again, now the next thing is we have to find the aggregated feature vector. So we have applied the CNN just like we have applied okay. So these are like multi-head attention. Why it is called multi-head? Because you are doing the attention at different head. So this is one head, this is another head, this is another head, this is another head, and then from each head you are getting the refined vector of the given words. And then you are combining it. And now, again, we are going to use one fully connected layer. Why? Because in this case, now I have seen the Z1 here, Z0 here, I have defined the Z1 here, I have defined the Z2 here, I have defined the Z3 here, I have defined like, these are the defined subvector that I have got. So it's like these are like refined, like I have defined x0 here, x1 here, x2 here, x3 here, x4 here, and so on. But I have not seen the relationship between x0 and x1. I have not seen the relationship between x1 and x2. Because at the end, this first representation is like you can say for the thinking only. So I have seen the sub part of the thinking, and I have applied the attention, and we got the refined feature vector. But in totality, I have not seen. I have not seen the full thinking thing. So I'm just seeing the sub part of this and then combine this whole thing. Similarly, I have done for the machine also. Now the goal is why not we should combine these all the information. The similar type of thing we were also doing in the case of like CNN type of architecture. Like we were applying convolution layer. Even convolution layer was also taking it was also having it was also the capturing the contextual information. But again, at the end, what we were doing, we were applying the fully connected layer. So that every information will be combined. So here we got the information from every part, and now you combine it. How? Combine with fully connected. So apply the fully connected. So again, concatenate all the feature vector, all the sub vectors, and make the vector, and then you apply the fully connected layer or fully connected layer over this, so that now it will learn, it will merge the information, and finally you will get this information for machine learning, thinking, and this this vector for the machine. So we are doing the similar thing, but now we have multiple head, and each head uh, is taking care of one part of the one part of the bigger vector. So we have this x vector, x1 vector. We have the x2 vector, and now we are giving small part of this, uh, and then we are finding the attention of like every part is getting refined separately, and then we are combining it, and finally we are getting this is the final feature. So from x1 you will get z1, from x2 you'll get z2. I should not confuse you with this x1 x2 z1 z0 z1 z2. It's like different. It's like we're talking about the part. Here I should not take in this way. Maybe this z2 and this is z1. So in totality, I'm getting this refined feature vector. But for getting this, first I'm dividing into multiple parts and then applying the attention. You can see here. So we have thinking machine. Then we have these. We got the words. We got the embedding vector for thinking, for machine, and then we have applied 8 different. Like we splitted this X into multiple parts, and then we have applied one attention for one part, like this. And from every attention, like you will be calculating, you'll be having the fully connected layer for Q, K, and V, and you will be calculating Q0, K0, V0, then for this K1, K1, Q1, K1, V1, then up to Q1, Q7, K7, and V7. And then from one first part, you are getting Z0, that's the defined vector, sub vector. Again, from this, you are getting Z1, then up to Z7, and then you are just combining, merging, concatenating these all the things, and then applying the one fully connected layer. That will give you final set. So here your this is like multi-head. So we have multiple head. This is one head, another head, another head, another head. So one head is just doing the attention, and you know that you can do it in parallel manner because you have the GPU. So that's why this process is also fast. Your things can be done in a parallel manner, and one guy is just responsible for the one part of the given information, and that's good now because if you just give the responsibility, the big responsibility to one guy, he will be failed, or he will be not able to uh, control it in a proper manner. So why not we should give part of that? Why not we should involve multiple people, multiple guys, where each guy will can give the focus on one part of the information. So we have in the X, we have a lot of information. We're just dividing it and assigning to different guys. So this is like one guy means like it's like attention. So we are assigning this to one head. This assigning to another head. This assigning to another head. This assigning to another head. And now every head will do the things. And at the end, we suppose I'm the supervisor. So my suppose I'm giving the task to the different BTech students. Now every will like I'm just dividing big problem into a small problems and then giving to everyone. Now every PhD BTech student will solve the problem, and then they will come up with the solution. And then at the end, our my job is to combine these all the information, combine these all the solutions so that I can solve the big problem. Okay, because I have only one problem, but I have divided into multiple parts, so that there will be like it will be like load distributed. Your load would be distributed, so there will be no too much load on one of the head or one of the guy. Okay, so you can see the visualization. Maybe after doing this, you can see here, maybe this is layer 5, attention. Maybe you can have a multiple layers in that. And if you see the visualization here, it's say there's it here, and maybe we have multiple heads. So maybe if you see one head, so you can have, or one or two heads, you can have like this type of structure. Like suppose this is the example. The animal did not cross the street because it was too tired. So we have divided into multiple, we can say, embeddings, multiple. It's not exact word because we have, suppose this is the, but again, this is, we are just converting our sentence into multiple parts. So most of the time we take word as a input, and then we convert into embeddings. But you can also take the part of the word also. Maybe you can take part of the words, or maybe you can also take two words maybe in a combined form. That's possible. It's your choice. Like wherever you are going to train it. Now you have to decide like how I'm going to tokenize the input, how I'm going to convert the words, like the sentences, into the vector. So what is the so that you can decide it. But in most of the cases, we take one word as a one input, and then we convert it into the embedding. So you can see like when I do it, and then we find the attention metrics. So you can see like here the it. This it part is correlated with the animal part as well as the street part. So even for us, if I say, hey, the animal did not cross the street because it was too tired. So you can easily say this it part is referring to the animal. But for the network, for the model, when you are calculating the attention, it does not know in advance, because the this part is also there, street is also there. So that's why this it is giving to it's giving attention on the street also, as well as the animal also, because for the net for the this that attention metrics, or for the this deep learning stuff, it's not easy goal, it's not easy task. For us, you can easily understand because we have been trained in that manner. So again, you have to train your model in that manner so that it can understand this context. So wherever I'm saying, hey, this it was too tired, so it has to correlate this thing like with the previous words. Okay, so say, hey, it is related to animal. but it may confuse you with a street also. So that's why you can say here that where this it is also connected to this. It's giving the weightage to this street also. Now, if you again see some other attention, so that's why I'm said like you have divided into multiple head. So these are divided like even if you have the has been divided into multiple parts. Suppose you have eight head. So then we will be having like we have divided the information of the into 8 different parts, and now you can see like what is happening in every part. So maybe if in some part you can see like this it is again giving attention to maybe it's connected with this like because it's showing the it's not you're not showing the full word at a time, it's just showing the part of the word, and then at the end you are combining it. So your model can like every attention matrix will give you different type of like different type of information, and then you are using that information and then combining you're refining the particular parts. So again, so that's what I'm saying, like if you visualize it you'll get to know like how it is happening, which part is giving more attention, which part is giving less attention. And again, initially it will give you anything because initially it does not know the proper like how should I give you the best information because it has not learned anything. So initially, it will give you a maybe not a proper thing to you, but while training, after some time, if you, once you are satisfied with the result, then you can even try to visualize the layers, like try to visualize the attention metrics, like where it is giving more attention, which part is giving more attention to which part, and like that. Now the next part is uh, in the transformer. Uh, Till now, we have not seen any this positional type of information. Till now, like we have just seen that like we can make the matrix and then we can find the correlation this attention matrix and then we'll multiply it. So if you just see the transformer, it's like permutation invariant. There is no meaning of the sequential thing there. So even if I'm saying hey, I'll give x1. I'll if I say hey, I'll be having x1, x2, and x3, x4. Now I can take x1 here, x2 here, x3 here. Now I know that order is x2 will come after x1, x3 will come after x1, even after x2, x4 is come after x2 because this is like x1 is for high, x2 is for how, x3 for R, and x4 is for U. Now U is coming after R and all the previous words. R is coming after how and all the previous words. So there is sequential information. But in this matrix, while we are going to calculate the attention matrix, we are not putting that constraint. We are not, because here, like in this attention matrix, if I just swap the x1 with x2, if I swap the x1 with x2, like I say, hey, I'll take first part as x2 and second part as x1, and then I'll do the refinement. There will be no any effect on the result because it will give you the same result. So that's why this is like this particular part is like permutation invariant. Even next other parts are also you can take in any order, you'll get the same type of information because your order does not matter. Whatever order you are taking, it will give you similar type of information. Even I can take x2 here and x1 here. Yeah, you have to take care of this thing while doing the multiplication, while doing multiplying with the v also. So if you're taking x2 here and x1 here, or x2 here, then we have to take this thing also in the same order. But order does not make any, it does not affect anything on the final result. But let me just tell you, whenever you are dealing with the sentences, you know that order makes, or order is the main component. Because if you disturb the order, the meaning would be changed. Or maybe whatever meaning you were getting, now it's not giving you any meaning. So if I say, hey, hi, how are you? But if I write hi, you are. Now there is no meaning of this sentence. So order is very important. And since transformer is not considering that, then why not we should involve this? We should involve this order information because this is very, very crucial information. Okay, because this will help the model. Once we give the order information, then the thing is like by which you can determine the position. Like if it's coming here, it is having some this type of information. That means you can say, hey, this is coming from this position. So we should be having that information involved here because that is required because we also want to capture the sequential information. And if you have the distance information or if you have the position information, then you can also find the distance between different words, like how far these two words are. So till now there is no any there is no any we can say the position information involved here. But if you have position information, then we can determine like if you are having some this positional information involved, then you can easily determine like hey what is the position of this word, and we can also find the distance between different words. So let us include that. Let us introduce that position information. So till now, what we have seen, we let's take the example of that translation task. So we have given this this sentence, and where these are the words. So we have first we convert into embedding x1, x2, x3. X1 is for this, x2 is for this, x3 is for this. And now what I'll do, I'll apply the positional encoding. So now I'll take one vector. So I'll be having the different vector for different position. So I'll take like this is the positional encoding, and I'm just getting from somewhere. So suppose I got T1 for the x1, T2 for the x2, and T3 for the x3. Now these T1, T2, and T3 are containing the position information. And now what I'll do, I'll just combine this x1 with T1, x2 with T2, x3 with T3. So combining x1 with T1 will give you x1. Combining x2 with T2 again will give you the refined feature vector. This will give you the again new feature vector. So now if I say like in x1 and x2, now whatever x1, x2, and x3 I got, it is having the positional information because I have incorporated here. So now this is like addition of the actual word information plus the position information. So in the paper, they have taken sinusoidal wave for defining the position. So what they have done, they have taken sine wave for the even position and cosine wave for the odd position, and they took this frequency, and this is the value that they have taken in their paper. And with the help of this, you can make the position embedding every for every input vector. So like this. So maybe this is the even position. So we at even position like 0, 1, 2, 3. So maybe whatever dimension of the input. Suppose you have 128 dimensional vector, or maybe I just take a d-dimensional vector. That's the vector for each input vector. Like suppose hi, how are you? So for hi, suppose we have 128 dimensional vector. For how also we have 128. So whatever dimension is having for that vector, we need the same dimensional vector for the positional encoding also, so that we can add those two vectors. Okay, so here we have 128, or suppose let us assume that d-dimensional vector. So at the even position, we have the even and odd position 0, 1, 2, 3. So at the even position, I'll take the sine, and at the odd position, I'll take the cosine. And every time this term, like your this frequency term is getting changed. So for first two term, this frequency is same only. Uh, Frequency is same only, but we are taking sine and cosine. So we'll get two different values. One for sine, one is for cosine. Again, for next two, we'll be having different frequency, but for sine and cosine, we'll be having the same only. So suppose you are taking W2 and W2. So now W2 will be for the sign, for the even position, and for the odd position, we have cosine. So in this manner, you are going to generate the vector. So if you have d-dimensional vectors, then half of the vector would be coming from the sine, and half of the vector would be coming from the cosine. And it's like in an alternate manner. So first cosine, cosine, sine, cosine, sine, cosine, and so on. So if you just do it, so you can, and suppose you are going to make 128 dimensional vector. So you can see here. So this is the dimension of the vector. And suppose you are generating 50 different position vector. So what I said, like T1, T1, T2, T3, these are like you are generating 50 different vectors, so that each vector will be assigned to the particular word. So one vector is assigned to the, suppose T1 will be assigned to the first word, T2 will be assigned to the second word. So these are like position vector which are going to added in a particular words. Okay. So now if you just plot it, so you can see here. Now this first part is for zeroth position, then second part, then third part, fourth part. So now if you just carefully see, every part is having distinct values. Every part is having, if I just consider one vector here and here, now all these 50 vectors are different. You can see like by the color this values, no? So every, like in this first, everywhere there is white. The second we have this and then white. So again, so things are getting changed. So every vector is having, and these are the range, these are the values that we have in that, in the given vector. So it's like this is saying that in the for the first case we have 0, 0, 0, 0, 0, 0, 0. So that's like position 0. Now, if you consider the first position, then we have zeros in most of the cases, but we have some values here. That may be like some maybe some positive values. So in that manner, if you just plot it, every vector is giving the distinct. Every vector is distinct. That means all those 50 vectors are distinct. So now one vector would be assigned to the one one word. So let's see. Let us go through the example. Let's see this thing again. Considering one example. Suppose you have given this word I am a robot. Okay. So let's. This is the formula. We have the same formula. The same formula we have written in this manner. So we have said, hey, this is the 2i means like it's like even position, and then 2i plus 1 is like your odd position. So whenever I have even position, then I'll take the k, that position number, divided by n 2 to power I divided by d, and this like sine of that. And then if you have odd position, then this part will be same only, but I'll take cosine. So let us see here, and let us apply this formula here, and then let's try to get like what we are getting, like whether we are getting distinct or not. So suppose I have given I am a robot, and for I we have 0. This is the 0th position. Then M is like first position. It's like we also say this as a token. Okay. So this is 0th token, first token, second token, third token. And now we are going to we are going to generate the positional embedding. So suppose in advance, I know that I'm having the vector for each. Just take this example only. So suppose we have four words. So I'm having 4-dimensional vector for each word. That means our D is 4. Okay. And n equal to 100. Suppose we have having 100 different words. We have having 100 words in the given input. Okay. Now I'm going to calculate this positional embedding. So again, so I'll for this k we have done. Now I have to use this formula. So whenever like so I have to generate 4-dimensional vector for every position. So suppose we have to generate for the 0th position. So in this case, k equal to 0, and I'll now these I have to generate 4 values. So first position is the even position, then we have odd position, then even position, then odd position. And at this point, at the first position, first and second position, the things will be same only. So suppose this is the I equal to 0, then this will be also I equal to 0. But only the thing is like, in this case, I'll be using sine, in this case, I'll be using cosine. So just use the formula. So sine and your k is 0. So if you have k equal to 0, so sine 0 will give you 0. At the second position, cosine k divided by 2 k divided by n 2i divided by d. So k is again k is 0. So again cosine 0 equal to 1. Now this is the first position. This is the first position for the even. This is the first even position, and this is first odd position. Okay, so I equal to 1 here, I equal to 1 here also, because this is representing the even first even position. We can say second even position. So we started with 0. So 0, this is 0th even position. This is 0th odd position. This is first even position. This is first odd position. Okay. Again, in this case also I'll be having, again apply the same formula. 0. So in this case, here also k equal to 0. So sine 0, 0, cosine 0, 1. So now you got this first vector, that is 0, 1, 0, 1. Now this is the vector for, this is the positional vector for the I. So whatever vector, whatever feature vector or whatever the embedding for the I will be having, so we'll take that, and so again we'll be having the same dimensional, because you have to, that's why we have taken this 4-dimensional, because I was also having the same dimensional embedding vector. So now we will take this and we will add this 0, 1, 0, 1, which is the positional embedding. Now let's go for finding for k equal to 1. So if I go for k equal to 1, so now your k is 1. So again, if you apply this formula, so I'll be having sine and k equal to 1 divided by n 2 to power I. Now I'm just looking the 0th position. So this will be 0 only. 2i equal to 0. 2i, so I is 0, so 2i will be 0 only. So n to power 0, that will give you 1. And 1 divided by 1, that will give you 1. So sine 1. So you can see you are getting sine 1 here. And that is like 0.84. In this case also you're getting the same thing, but we are going to apply cosine. So cosine 1 equal to 0.54. Now in this case, your I equal to 1. So now you'll be having sine k is 1 divided by n is 100. You can see you have taken 100. And then 2i. So 2i is 2 into 1. I is your 1. And divided by d. So d is 4. So if you take this, so 10 to power 2, that's like it will give you 10. So 100 is like root of 100. So that will give you 10. So we'll be getting sine 1 by 10. So sine 1 by 10, you are getting this value. Even in this case also, you will getting the same value here, but now we are going up cosine. So cosine 1 by 10 will give you this value. So in this manner, you can calculate the value for like the vector for each position. So this is for first 0th position, then first position, then second position, then third position. And now if you see it, every position is having distinct values. This you can see here. Everyone is giving you the distinct value. And now you add it in the original embedding vector, and then that will incorporate the positional embedding. Now the thing is, you guys can ask, hey, why we have taken the sinusoidal wave? So actually that paper has taken. And the reason was, reason was that it is giving you some sort of distinct or different vector for every position. And that's why they have taken it, they observe it, they empirically studied it, they have empirically studied it, and then they have said, hey, go with the sinusoidal. And it's like easy, even easier function. So why not we should take the easier function, which can be controlled easily. So they have taken it. But again, anybody can say, hey, I'll not take it. I'll go with some other function, which can, again, I'll make sure like that function should also give the distinct value for like, we should give the distinct, distinct vectors every time. So that I'll make sure, but I don't want to take this sinusoidal. This we can say it. So then later, what people have given the idea. So if people are interested, people are interested to take different type of this function for getting the positional embedding, then why not we learn it? Now just give this task to the model only. So instead of fixing, because again, this is very hectic process. So somebody is taking sinusoidal, somebody is taking some other function, somebody is taking some other function. Then this is again hectic process. Then why not we make this as a learnable? So later they have also, if you just see in the you can just find it out like in many architectures, you can see like they have just learned it. So we'll say to model, hey, you learn the vector. So I'll not give you the fixed, I'll not give you vector from any fixed function. Because again, fixed function is having pros and cons. So I don't want to give you the fixed function. Instead, you learn it, and you by yourself you learn the function like which type of function I should learn for making the vector, so that you it will be unique for every position. So it can be learned also like a parameters. So now we have seen this whole picture. You can see here we have thinking, machine. We started with this, converted into x1, x2. Then we have added the positional embedding, got the x1, new x1 and x2. Then apply the self attention, get z1 and z2. And then again, in the encoder part, there is one layer that is called add and normalization layer. So that part is still left. So we do normalization, some normalization here. Again, you got the z1 and z2. Again, you are defining it. So you got the defined vector. Then pass through the feed forward network, fully connected layer. Do again apply the add a normalization layer. And now this is the encoder block one. In this manner, you could be having multiple encoder blocks. So I think I'll stop here. And in the next class, we'll cover the remaining parts like normalization, and then we'll go for the VIT. I'll I'll allow you to speak.
Hi, sir. Sir,
Please.
that I is equal to 0, and in the second
Uh,
column also I is equal to 0 there. Instead of
uh.
that, can we have I is equal to 0, 1, 2, 3 continuous number there?
No,
We can
actually,
have. We can have, I think.
no. Uh, this I equal to zero and this I equal to zero. Na.
Hmm.
This these are like different things. This I equal to zero is this is at the even position, and this is at the odd position. So at the even position, you have different function. You have sine function. At the odd position, you have different function. That is cosine function. So that's why even if you take the same values, now it will give you different values. You can like whatever you told that you suggested, you can also do it.
Ah,
But
okay. Okay.
but since I know that if I take even same values, I'll get the different values only because we have different functions. We have sine and cosine.
No, so the index, I'll maintain the index as a continuous number. Index I is equal to 0, 1, 2, 3. But the index of the
Mm.
word I'll keep on using same for all the values of I. If for example, for even number I use sine 0. For all odd numbers I will
Mm.
use cos 0. I'll keep on doing the same
Mm.
thing. By that I'll remove the confusion what I got in the I is equal to 0 or I is equal to 1 or something like that. I can keep on doing the same continuous number. No, that's possible.
You can
Yeah.
do it,
Okay. 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 Sir. Okay, sir. That's
but yeah, you
yeah.
can do whatever you want. You can do it. It's
Yeah.
just
Okay.
play
I
around. You
got it.
can play around these values,
Yeah. Okay. Okay.
but they
Okay,
have
sir.
done in this way in the paper.
Okay, sir. Okay. And if we go back to that it where we have mapped it to a different words in the sentence,
Hmm.
the slide,
Hmm.
if it's in the slide.
Yeah,
Yes, sir. Here,
this
yes, sir.
one.
Here, yeah, yes, sir. So, do you suggest to go for a pre-processing before we feed all these words into these the model, the transformer model, multi-head model?
Yeah, we do some pre-processing.
Okay,
If you just
pre-pro.
work, if you work in NLP space, now we have a
Yeah,
lot of methods for the
pre-pro.
pre-processing.
Okay,
Even
sir. Okay.
embedding that you are getting, now embedding
Mm,
is that embedding layer is also it's like one. It's also one type of function that you are applying. So either it will be fixed function or you even it can be learnable function also. Sometimes we use the transformer model even the transformer model for doing this. So transformer model also you can also design your transfer or you can also train your transformer model for converting your words into the vector word
okay,
to
sir.
vector. You can find it like you can get the paper.
Yeah,
So
yeah,
that is
right.
again they have used the transformer model only for training this for learning this embedding like
Okay, sir.
how should I give the very good embedding so that it will be easy for the model to learn in a proper manner. So we can
Okay,
do a
sir.
lot of things at the starting.
Okay, sir. Okay. If you go back to slide above, sir, above, if you go back to slide above, where you have mentioned small part of the word is been, entire word is been divided into small parts, and later on it be converted. Here, that one, that above the next before the slide.
This one.
Yeah, yes, sir, this one. I think this is yeah, this is where you have drawn three circles, small circles there before X.
Hmm,
There is a X
hmm,
and you are drawn thinking you are divided
hmm,
that into three small words, and then you try to correlate with others. Does it lose the sentence meaning, sir, there, or otherwise the contextual meaning? If not text, some
hmm.
contextual meaning does it lose?
Yeah, it will lose. So that's why at the end we are using fully connected layer to combine all those contextual information. If you see at the end, what I
But in
said
the
that.
morning, but in the morning session, what we have learned is now one word,
Hmm,
for example, hi, how are you? Hi is being
hmm,
correlated with all the three other words there. Okay, and
hmm,
by that I could able to maintain correlation with the whole sentence. Are we maintaining similar
hmm.
kind of correlation here also?
Yeah, actually for each, when you are dividing, suppose for high, you got maybe 128 dimensional vector. Okay, now this is the representation of your high. So in the morning class, what I said, like for like every vector you'll be using. Suppose you are focusing on the x1, then you'll be using the vector of the x1, and then you'll be finding the attention with all other vectors. Okay. So we are just looking the full word, and then you are finding relationship. Now in this case, since I have divided into multiple parts, so now the this small part is not talking about the full word, but it's just talking about the part of the word. And I just if I'm taking the first part of this word from high, again I'm taking the first part of the word from the how also. So if I'm going to find the attention, so I'll be finding the attention with the help of first part of the words, like first part of the vector of all the words.
Uh-huh.
So every word, for every word, I'll be just taking the first part only because every word is getting converted, like it's getting divided into similar manner. And then
Mm.
like for every part I'll be applying the same type of mechanism like finding the attention query key value getting the attention matrix and then defining the vector. So what we are doing, we are defining each sub part separately.
Okay. Now, do you divide here each word in an equal part, each word in equal part? For example, hi is been divided into three parts, and how are you is how is been divided into three parts, and then only
Yeah,
the first part is
every
the first part is related to only first part of the how, or is it the first part of the I is related to all the parts of how? How is it actually?
I'm taking first part of every
Hi.
words and then I'm
Fir-
doing the for example we have hi, how are you? Then
mm,
for getting the first attention, for getting the first defined vector, sub
mm,
vector, we're
mm.
just taking the first part of the hi, first part of the how, first part of the hi, r, and first part of the u. And then using these all the things for getting z0. You're getting my point. So
Yeah,
every
I
part
got.
is like, yeah. So every part is getting defined separately. So I'll be doing the first part refinement of the first part, then I'll doing the refinement of the second part, we'll doing the refinement of the third part. So in every part, we are applying the attention matrix.
No, but does
And I
but that,
understand your question. Like you're saying, hey, that full contextual information we are missing here.
yeah.
So that's why at the end, what we have done, we have whatever defined sub vector we got from every part. Now we are just concatenating all those vectors because I know that only one part is not sufficient for telling the meaning of the word. So then we have to we have to combine all those subparts so that I can be having some meaning. I can be having the meaning of that word. So that's why we combine it, and then again we apply one fully connected layer so
Is
that
it
again,
when when
yeah,
when you
yeah.
when you say combine, sir, is it element to element combine, or is it entire matrix to matrix combine? Is it column to column
No,
combine?
no.
How is it
Combine means like suppose
concatenation?
concatenation. So in this case, suppose we have two words like thinking and machine. So
Mm,
for thinking, you have divided into multiple parts. Suppose 8 parts. For machine also you have divided into 8 parts. Now
mm,
for the first part, you took the first part of the thinking and the first part of the machine, and
yes,
you
sir.
have applied the attention. You got
Okay.
the refined feature vector, refined sub vector for the thinking, refined sub vector for the machine. That is your Z0 and that is your Z0. So Z0 in this first part is for the thinking, this part is for machine. For the
Mm,
sub part of that.
mm,
Similarly, you will get for the second part, that is your Z1. Then you have
mm.
Z2, Z3, Z4, Z5, Z6. And now you
Okay,
have
sir.
combined it. You are just putting one after another because
Okay.
now this full vector, now this
It's a,
full vector combining up to this, now this is
mm,
giving you the meaning of that full word.
mm,
Even the second full vector is giving the meaning of the your machine.
mm.
And again you have to also, like, we have not seen the relationship between this Z0, Z1, Z2 and Z3. That part was missing because we were just processing each part separately. So for capturing that relationship, that contextual information, again we apply one fully connected layer. So it will, again, this fully connected will take this and then it will learn. It will try to refine it or try to capture the contextual information. And finally, we are getting this. Now, this part and this part. So this is the final Z that we are getting here. The first part is the refined feature factor for the thinking, and second part is the refined feature for the machine. Now,
So
this
the
thing we were, yeah,
the final result, sir, final result what you're telling is that does
this is from
thinking is,
one layer. This is
yeah,
this is from
yes,
the
sir.
one attention yeah, one attention layer, huh?
Okay,
That's
sir.
in the multi-head, huh?
Okay, sir. Does the thinking is correlated to machine there in the Z, the final Z there, final Z value? Does the
Yeah,
thinking is
because
correlate?
because subpart at the subpart level we have done it now. At the
No,
subpart level we have
no, but
refined the
as I see there, sir, we have just only divided the words into multiple parts there, and we have divided them into equal parts so that both the words are getting divided equally there. And what we are doing is
yes
we are only adding thinking part to thinking, machine part to machine. We are not trying to correlate thinking part with machine or machine part with thinking there. We are keeping it independent there. Okay, and how is it?
no it's not happening actually. Like for thinking now, suppose you x1 is your thinking and this is for x2. Now you
Mhm.
have divided x1 into 8 parts. So now you
Eight
are
parts.
taking first part like x11 and
Mm,
x211.
mm.
This is your first part. Similarly, you have x112, x22. This is the second part.
And
And
similarly, we
each
have eight
part
parts.
is going through the attention. Yeah, and each part is going through the attention
Oh,
mechanism.
each part is going through the attention. Okay, 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 sir. Okay,
Uh,
there each part is going through
and then
attention. Hmm.
yes, yeah, and then you are
Hmm.
getting that Z, this refined of this and refined of this,
Hmm. Hmm.
then
Hmm.
refined of this, refined of this, and then finally you are concatenating this thing. So from this
Hmm.
part, first part you are getting Z0. So
Hmm.
this first part is refined of the this part,
Okay, okay,
and the
sir. I
second
got your
part is the
point.
refined of.
Okay, sir. Okay, I got your point there, sir. So, what is the key query key values there, sir? I got that. Are they related to input vector there? Query keys and values.
So these are like just you are getting
Query
this
keys and
thing. These
values,
all
sir.
the query key
First line.
values.
Uh, the
Where
slide which we a slide which we started with this one no, no, query, sir, query, you gone too far, actually, you gone too far. You can't do
Oh,
first the query, sir, query part. Next,
this
yeah,
part?
this one.
Huh.
Yeah, this one. Yeah. What is query keys and values there, sir? Actually, we have two words there, thinking and machine. That's what we are going to give as an input there for embedding. Means we are trying to make use of transfer. We are discussing here in the context of transformer, and we are trying to
Hmm.
add a head there,
Hmm.
multi head there for developing a
Hmm.
correlation. What is query,
Hmm.
sir? How does it actually used for developing a correlation with thinking and machine there, sir?
No, query actually, we are not doing this, we are not applying this attention in the original space. Instead, we are transforming it into the feature space that we have seen in the morning class. So we had, like, if you just recall, you were present in the morning class,
No,
right?
I was there, sir. I was there. I was there. I
So the
understand, sir.
first
I
fully
understand the
connect,
morning class.
uh, yeah, first fully connected layer was giving you the Q. I think K or Q, maybe
Ah, okay.
K.
Okay, in that
Then it was
sense,
giving
okay.
you the K,
Mm-hmm.
V.
Mm.
Okay, so we are finding the attention, but it's in the feature space. So these
Okay.
Q, K, and B are coming from the same axon only,
Mm.
but after getting transformed, like after applying the fully connected, after applying three fully connected layers. And
Okay, sir.
that's
Okay.
why the learning was involved. Otherwise, if you just go with the fixed function, then there's no learning. If you just this simply correlation, finding correlation and then defining the vector. So
Okay. Okay.
this was like the main part that they have introduced in their paper for making this as a transformer.
Okay, sir. This completely the one element actually where we convert into um
Yeah.
uh, yeah. I got your point, sir. Yeah. Sure.
Still we have not covered, like still we have few things to cover for making this full block. So those things, like we'll cover in, like layer normalization is still left, and then we'll go for the complete architecture.
Now, what is the
So
position encoding, sir? What actually it is used for position encoding, sir? There,
we're
we
just
have
giving the
one.
position. We're just giving the position because in your, like, embedding, when you are generating the embedding, you're
Mhm.
just directly getting one word and giving the embedding. So
So
there's no position involved with
it's
there.
no, it's a one more data that we are storing along with the text data. For example, if I give thinking as a one word as an input to it, input to a model,
Hmm.
then along with the
Hmm.
text, along with that thinking word, this position encoding will also be stored and processed in the model. That's what you mean to say.
Yeah. So this is the thinking, the vector for the thinking, and then you are taking one extra vector
Okay, one
of
more
same
extra
size
vector.
vector,
For position,
and that
for
is,
position,
yeah, for the position, and then you are
position
adding these
one.
two terms.
Okay, okay,
And now
okay,
this is the new thing. And here I can say, hey, now in this word we have the information of the word along with the position information.
okay, sure. Now I got your point. Yeah, thanks a lot, sir. Thank you.
Okay, so in the next class we'll complete it. Thank you.